Okay, so here's where things get especially hard. And they are especially hard when you use prime numbers as the clock size. So thanks to some special properties of prime numbers, with a prime clock size, there's only one solution to each modulus equation. With a brute force search, you could go through all of them in a couple minutes, but what if the clock size were a 50-digit prime number? That's when you have encryption. Whenever you have a problem for which the only way to solve it is randomly guessing or brute force search, over a large range of values, you have a candidate for encryption. So this is where things get really tricky. I try to come up with this outline, especially for you math types out there. Maybe if I explain this in the sense of balancing an equation, you might feel a little bit more comfortable with what's going on. So before we go to that widget, let me just explain what you're about to see. You're about to see two people using something called key pairs. In this scenario, pretend a guy named Bob has a secret. So Bob's job is to create some sort of public number. He's going to do that by taking a public key, so everyone knows this number, and he's going to times it by a private key that he doesn't tell anyone about. Then he'll do modulo using a public modulo number, okay? And that will give him this public number that he can pass to Alice. So now Alice is sitting there. She has this public number from Bob. She's going to times it by a private number that she has. She's not going to reveal it to anyone. Then she'll do the modulus with the same one that he did, so same public modulus. And that will give her his private number right over here. And imagine if that's the only thing you needed to get was just a single number. If we're talking about a Caesar cipher shift, then you have that number of how much the alphabet is shifting, and then you got it. You could break the ciphertext and read the message inside. Now, it's a little more complicated than that, but just to feel comfortable with what we're talking about in class at such an introductory level, go with this. Go with this idea that Alice, the one trying to get a secret from someone else, all she needs is this equation, which is a balanced equation. You have a public and a private number, and then you have a public and a private number. If this is balanced, she'll be fine. And for Bob's case, he has 1, 2, 3 public numbers he's working with, but that's because he's the one sending a secret out into the public. So it's a little trickier on his end, but still very secure. And then if you want to take the hacker's perspective, think about guessing at this private number right here or right here. Either way, if you guess a number that's different than the actual number, you're going to get a different private key at the end. So when you guess a different number, you get a different number, and thus it's worthless. So don't get tripped up on the math today. What I'm saying is, like, this is math magic. This is what's allowing our world to work in such a crazy way. Now, quantum computers can easily break this. That's something we have to think about. So technology is going to need to change with that in mind. And at the end of the day, for the people, the students who are really understanding what's going on here, I would say, like, this is the kind of stuff that's only for the most powerful wizards and sorcerers to use. If you can understand magic like this, you might be able to create the magic like this that we will need in the age of quantum computers. I would love to talk more about post-quantum cryptography, but for the scope of this class, we just don't need that. All right, so let's go back here. We're going to use this link to see all these equations in action. Okay, so here we are. Now, I clicked all because I think this is the best way to approach this widget. That way you have plenty of time to think. You can write notes on a piece of paper to try to work this out. You could take notes on the formulas I just showed you over here. So let's put what I said into practice. Bob is the guy with the secret. So Alice wants that secret. Let's say Alice and Bob agree to a number, let's say 11. It could be any prime number here. So we're going with 11. So she has that public modulus. She'll go ahead and pick a secret key. I'm going to go with 5 here. So now we go over here, and he needs a public key. Where does he get that? Well, from Alice. She's going to come up with the number 9, and then again, everybody can see it. So here's our Eve, the eavesdropper. So far Eve knows that the public modulus is 11, the public key is 9, and then she doesn't know anything else yet. So Bob comes over here, and he's going to pick a secret number of his own. Let's go with 5. So Bob takes this private key and the secret number, times them modulus 11 them, and that will give him this public number, number 1. He's going to go over here and give that number 1 to Alice. She takes that. She uses the public number and her private number, mod public modulus right here, and this will give her Bob's secret number, 5. Is it correct? It is. And that is basically how public key cryptography works.